Okay.
So may I start?
You can start, yeah.
Yeah, can you hear me? Yeah. So today I hope it will work for me. So I try to write on the whiteboard, and the aim of my talk is probably, well, hopefully to convince you that the integral transformation I define is maybe useful for, I don't know, probably for some of your purposes. So what I will be talking about, I will be talking about Appell integral. Well, Appell integral transform. So how we will be, the notation will be sort of A, and then eta will be some random variable. So that's an integral transform that can be applied to a function, but does depend on some random variable eta. Okay. Right. So before we start, we should choose the language. Yeah. So first, what I would like, so choosing the language. So eta is our random variable, and suppose it has all the moments. So random variable has all the moments. Or you can say that it has all the cumulants, for example. So if it has all cumulants or all moments, what can we say about this random variable? That it has a moment generating function, and we can write the moment generating function as the mathematical expectation of u nu. And here will be your moments. Or you can write it also as a cumulants. Sorry, that's the exponent, of course. And then there will be your cumulants, sum from 1 to infinity, km u, and divided by n factorial. So here we're sort of in the combinatorics realm, yeah. And if all the cumulants exist, then we can think about the process as a sort of a line of cumulants, for example. Or of course, you can go to characteristic functions, and then instead of here, well, we'll see bilateral Laplace transform. So instead of bilateral Laplace transform, we will see the characteristic function and operate with that. Right, so that's the first. So we can talk about, in terms of cumulants and moments, probably as functions of cumulants. Moments can be expressed as a Bell polynomials in cumulants, or we can talk about it in terms of characteristic functions. Then probably we can use generalized function and so on. So that was choosing the language. The second one, I would like to mention Escher transform. So I don't know if people probably coming from some sort of financial mathematics, then they might heard about Escher transform. This was introduced in 1932 and was used by actually not, that's a very rare transform which came actually from practice. It came from actuaries who introduced it all before this sort of measure change in 1932, right, to use in actuarial calculations. And that was introduced to remove the drift. So before all, like shows 1932, that was the Escher transform. And we will talk about, and this can be written as e power ux divided by familiar moment generating function. Okay, right. So the third one, finally, we go to the Appell integral transform. So sort of we are ready. So what is it? Yeah, I promised you that it will depend on some random variable. Then it will depend on some, well, take function. So what is it exactly? So first of all, well, let us choose the language of cumulants here. Of course, we can choose this language and nothing will change except that you have I here. Yeah, and basically just operate in a different, I don't know, kingdom of functions. So, but now let us choose this language. And actually the reason for that is that I want to use a Escher transform in this form. Yeah, with moment generating function. So if I want to use this language, I have to go to, write a characteristic function here, and here it will be another I. So let's choose the first language, and that's why I'm writing the inverse bilateral Laplace transform of function g. Then I write my Escher transform. Du. So that's the Appell integral transform, and hopefully I can fit here another explanations why Appell now. So why Appell? So that's some sort of integral transform. Why is it called Appell? It's called Appell because there are Appell polynomials. Well known Appell. Well, I'm sort of writing, I think it's 2L. So Appell polynomials. How are those Appell polynomials defined? Actually, this is their generating function. So, well, one of the definition of the Appell polynomial is that this is the actual Escher transform is their generating function. So we have to generate n times with respect to u, and then substitute u equals 0. So that's a very well-known object. Examples of Appell polynomials are, for example, Hermite polynomials, Charlier polynomials, and so on. They're closely related to Levy processes because Appell polynomials build on Levy processes are martingales, and so on. Okay, so right. So if our eta, for example, so what is it exactly? So you can look at it, yeah. If you substitute Dirac as your random variable, you will receive this expectation will be equal to 1. So you receive just e power ux, which is the generating function for just x power n. So this is the most simple case, and the polynomials x power n are actually Appell polynomials with respect to Dirac measure. Now, if you take here normal distribution and plug it in, what will you receive? You will receive Hermite polynomials. So here, the moment the generating function will be just e power x. Here it will be e power ux minus u squared divided by 2 and so on. Yeah, so you can continue, and that's all very known. And that's why, well, yeah, and so, well, you can say that because here we have the moment generating function of Appell polynomials, this is called Appell integral transform. Actually, I probably will go a little bit, I will talk about it a little bit further. You can think what is the inverse Laplace bilateral transform of x power n. This is the nth derivative of the delta function. I don't have to explain why in this room probably. So this is if you take the inverse of x power n. So if you want to build up an Appell polynomial using the Appell integral transform, what you need to do, you need to take the inverse Laplace transform of x power n. You will receive your nth derivative of the delta function. And so to calculate the Appell polynomial, you have to differentiate the moment generating function n times. So in such a way, Appell polynomials are Appell integral transform of y power n. So it should be x, of course, x. So it's called Appell integral transform because this is the generalization of Appell polynomial. So why is it useful? For example, it's they can't. Okay, well, right. Only the middle board. Oh, I didn't know that. Sorry. Okay, right. So hopefully I will fit everything in. Okay. So right. So why is it useful? Because it's very easy to build up martingales. Right. And so before we start, let us remind you that if xt, for example, is a Lévy process, or well, we can actually formulate it in a more general way, but that's enough for now. Then the exponential martingale, well, actually, that's a martingale. Is a martingale. So that's very easy to prove, of course. I don't know if I have to do it here. Probably one line, so I can do it for you. Just a quick. So why is that? Because it's important here. So we take the mathematical expectation, we subtract and add, and then because the increments of the Lévy process are independent, so we can write, for example, this one, right? So then when you take the conditional mathematical expectation, you are left, these parts are canceling. So that's indeed is a martingale. Now, if this one is a martingale, then the Appell integral transform some proposition, if xt is a Levy process, then Appell integral transform built on xt applied to some function g from xt is also martingale. Well, this is obvious because if you can exchange the integration, this one is a martingale. So in this way, it's much easier, for example, to prove that Appell polynomials are martingales. So in such a way, we see that we have a tool to create martingales, and the only thing we have to do, we have to look and find out what kind of inverse bilateral Laplace transform. And obviously, we can also use for fractional derivative and fractional So if very well familiar with our g, our n, we receive the nth derivative of the delta function. So what would we receive? Instead of n, we have some alpha. Well, let's do yeah. So how would we do? What will be the inverse? To take the fractional integral of air transform, right? And then differentiate. So in such a way, we can define the fractional derivative of the delta function as the nth derivative of the delta function, but applied not to the function, but the, for example, yes, so yeah, so you can use in such a way you can use the fractional derivative of the delta function, which can be defined, and the nth derivative of the delta function part of the this instead of this, yeah, you take the fractional integral, right? And that's possible. I don't have time to write it down, but the answer, for example, for normal distribution will be some form of confluent hypergeometric function, which can be which also can be used. So instead of using only n cumulants, so what is Appell polynomial? Appell polynomial can be written, yeah, if you have first k cumulants, it can be written as the Bell polynomial of the first n cumulants, right? So if you know first n cumulants, you actually the minuses here. If you know first n cumulants, you can write Appell polynomial in such a way. If you have fractional, now n cumulates won't be enough. So instead of a polynomial, you will have some sort of a hypergeometric function in this case. So of course, you're very welcome to differentiate other moment generating functions. I mean, Escher transforms, right? For different processes. And what you will receive, using this fact, the simple fact that you have a martingale, that a transform, well, the Appell Integral transform actually gives you a martingale basically for free, yeah? Because it's very easy, you just put the mathematical expectation inside, and because the Escher, this is the exponential martingale, you receive immediately the martingale, yeah? So it's much easier. So in such a way, all you need to do to create a martingale you need is to find the inverse bilateral transform. Now, I especially said in the beginning that you can choose the language. So it's up to you. You can use this language of characteristic function. So you will be in completely different domain. There is no combinatorics. Well, there is, but if you will exist, but okay, well, you can, and so this is one thing I wanted to say, and just to finish, I wanted to add another, another theorem. So another problem which arises in different areas and familiar probably to you, financial mathematics. Okay, so there is a process xt. Let's say that it's a Levy process, some function g, and the question is how to build a martingale such that martingale, say, c from txt, such that at the final time t capital, it's equal to your function gxt. Using Appell Integral transform, it's quite easy to do. So why is that? So say lemma. So let's xt the Levy process, right? Now define function h from y as the Appell integral, the inverse, actually the inverse of Appell integral transform built on xt capital. So t is this special time to which you want to come as a martingale, okay? So you build your Appell integral transform on this xt capital, right? Of function h, and just a moment. So yeah, so this is the inverse, and then of g of y, and then dtxt defined as an Appell integral transform now on xt small. So here we have t capital, here we have t small, of newly defined function h will be a martingale. Why is it a martingale? We already know. And to prove this little lemma, what you only need to do, you need to check this condition, which is straightforward. Do I have time for this? Yeah. Okay, so I just, okay, so again is, so what is C from TXT capital? That's by definition, this is Appell Integral transform, yeah, built on X T, because we are looking at the final time T capital of H of xt, but by definition of H, right? This is actually of G of y, G of x, yeah. So just by definition. Well, of course, what we need here, we need a method to find out what is the inverse, yeah? What is the inverse of Appell Integral transform? But actually the inverse, I probably don't have time to speak about it in detail, but the inverse is actually here. And if we find, it's not always to find such a random variable. Theta equals 1. But it's always possible to talk about not random variables, but some something that probably can help us to calculate. So something that doesn't exist that helps us to calculate the inverse. So that will be, the inverse will be, instead of this one, what you need to do, you need to multiply by you have to multiply by this guy, and then this will be the inverse. In terms of, it will probably easier to understand in terms of the cumulants here. So basically, to go back and forwards, right? What you do, you if you want to build up on eta, you subtract cumulants. If you want to go backwards here, you just add cumulants. So here it's nice and additive. And yes, so if from x power n, you go to other polynomials, you subtract cumulants. If you want to go back, you add cumulants and go back to your x power n. So that's exactly what happens here, right? So probably we need a little bit more details on that. But, you know, when we talk in terms of cumulants, it's not difficult. Yeah, to find inverse. Well, I'm not talking that it exists, but there exists some formal methods which actually help us to calculate, and that's enough for me.
So it seems this is motivated by financial mathematics, in which C is the price of European security, like option,
for example,
European options. But for LV processes, there is another problem of uniqueness, like market usually is not complete. So you have so many martingales. Which martingale?
Yeah, well, this is just another martingale. Yeah, so I'm not talking about uniqueness here. It's all now.
But in principle, how to find the best martingale here?
Well, that's another problem for you. But yeah, of course, you can. Yeah, well, this is another problem. Yeah, this is a separate problem. I'm just saying that it's a way to construct martingales. And for example, in the case of fractional derivatives, it's basically a very easy, free thing. You receive a martingale, but it looks horrible. It's some sort of a hypergeometric function, you know, and inside there is a Levy process. And how on earth, do you prove that this is a martingale? And here how? Nice and easy.
But you know how to find the best martingale?
No, I haven't thought about it. I actually didn't think about, well, I know this problem is sort of, it's another problem, right? It's another problem. But I know that, well, I just thought, well, what can you do with that? Actually, there are another applications. Actually, this came from optimal stopping. And in optimal stopping, it can be used as well on some other random variables. So, and it's a nice way, just to change the measure, as a Escher transform actually was used, to change the measure before all this theory when you have to remove the drift and financial mathematics and so on. So that's change the measure, basically. So here we change the measure. And of course, when you change the measure, you can, apply it in many situations.
I think we must go to the last